Hi, this is Jeff Coronado from JCSE, and this is a session in Bridging the Gap, a sequence of structural engineering design tutorials that we have here in the office. So in particular, let's tackle this question. How do you find the capacity adjustment factors for sawn lumber? All right, so this is a question from one of our young engineers. So let's go ahead and tackle this. All right, so our question was capacity adjustment factor for sawn lumber. Okay, if you don't understand the difference or what sawn lumber is, be aware we do have other tutorials in Bridging the Gap that do cover that. Also, as you can see, the hint here, get all you can from the tutorial. Some young engineers, some engineers will just kind of want to pick and choose, kind of get a value out of something, but you're shortchanging your education, right? That's not how you learn. That's like I don't know, going into a textbook and getting one number or just following the example blindly, without really understanding the theory that goes into it. It just kind of ill-equips you to then handle future similar problems or even somewhat different problems. And really that's at the crux of Bridging the Gap. It's to empower you to becoming a structural engineer. It's so that you understand the thinking process that goes into structural engineering so that you can resolve not just this particular problem, but other problems that you will encounter in the future, not just the ones that you see tutorials for. So don't shortchange the tutorial. Get the educational value. Take notes on it, right? Make notes for yourself on where you saw different key things during the tutorial so that you can always refer back to it. So again, we've got sawn lumber. The difference between sawn lumber and other lumbers are covered in other tutorials. Leave us a note afterwards if you want us to point you in the direction of where that information is covered in other Bridging the Gap sessions. But this one is about sawn lumber. So for sawn lumber, we're going to use the National Design Specifications, which is NDS, just abbreviated NDS. We're going to go to the NDS Table 4.3.1. And here is an excerpt of that table. And this very much provides a roadmap. This is a roadmap that's an incredibly useful tool, almost a must, right? Almost something that you have to reference if you are designing a sawn lumber element or a connection to a sawn lumber. So let's take a look at this roadmap, if you will. So what do we have here? Tabulated values. Okay. Okay, so let's cover tabulated values here for a minute. So tabulated values are covered in other Bridging the Gap tutorials. Here's what I can say about that though. So kind of a little bit of a sidebar. In fact, let me write it down. So in timber, which is kind of unique to other materials that we use in structural engineering, timber primarily, if not exclusively, the allowable values that we use, the allowable stresses, are empirical. So these are values that we've obtained through testing, and basically that's it. It's through testing. It's actual practical testing. Timber is not a material that can be designed, in essence, using first principles, what we would call first principles. There's multiple reasons for that. I believe that's covered in another tutorial in Bridging the Gap, where we get into the homogeneous nature, or the isotropic nature, I should say, of timber, which is kind of what leads to that. But for right now, without getting into that other tutorial, for right now, I think the important thing is to know that for timber, we start off our design process with tabulated values. We just have to take it for granted, verbatim, that that's the capacity of the element. It's what's shown in tables, primarily given to us in the NDS. Let me show you here. So when you see this column, that column there, that refers to the tabulated values. So this is the first value that you're going to obtain in determining your capacity of your element. So for instance, let's take a look here at the first row. All right, so we've got, so we're looking at the first row. Let me clear this so that I can zoom in a little bit. Oh, interesting. Okay, so I've zoomed in. Hopefully this is more clear. So we were looking at that first row, and you can see that now if we're focusing on that first row, then here's the tabulated value. That's what's represented by the tabulated value. Look how this one says F sub B, and so that means bending. So this is the tabulated bending stress, the allowable tabulated bending stress for sawn lumber. That's what that value represents. Notice how that is different, or notice the difference with the variable to the left, which has a prime to it. And in fact, you will notice that here in this column, notice how all of those values, all of those variables have primes. So the prime is how we distinguish between the tabulated and the final design capacity. So initially, we start off with a tabulated capacity, which is this variable here, and then we end up with the final capacity of the element, which is this variable. But to get from the tabulated capacity to the final capacity, we have to go through these adjustment factors. Okay, so let's take a look at the adjustment factors that we have to go through. So first, you will notice that we've got this and this, which are exclusive to ASD or LRFD. So there you kind of have to know or make up your mind, decide how you want to design this connection or this element, whether you're going to follow ASD procedures or you're following LRFD procedures. So if you're going to follow the ASD procedures, then this column will be in play, and you will have to multiply your tabulated capacity. So you would have to multiply this tabulated capacity here by this factor in this column if you are doing ASD design. If you are doing LRFD design, then you would have to multiply again the same tabulated capacity, but then you would come over here and pick off these three factors. So you'd have to pick off a K sub F, which is a format conversion factor that takes you from the tabulated value up to, basically think of it as a nominal value. Then you have, as you typically have in strength design, you have your phi capacity reduction factor. And then there is a time effect factor, which is kind of a unique concept in timber. Well, there's a little bit of that in concrete, but still, this time effect factor is basically unique to timber, but you do have to take it into account for LRFD, whereas you'll notice it's not present if you are doing ASD. This is exclusive to LRFD design. However, with that, let me say this. By and large, what I have observed in timber design is that it is very unusual to see timber design being done in LRFD. For as long as LRFD has been around, I would still say that the standard of the industry is to use allowable stress design. You will see that a lot of kind of peripheral concepts that are touched in timber design, such as connectors, proprietary products, all of these other things are pretty much exclusively dealt with in allowable stress values. So you will find yourself duplicating a lot of work. In essence, if you try to do it LRFD, you almost also have to do it allowable stress, because in many other ways, in many other instances, you're going to have to get LRFD values. Let me give you a simple analogy. It's kind of like if you design a beam for ultimate strength, but then the reaction you need to know for allowable stress purposes, because the supporting element, for the supporting element, you need to introduce that load into the supporting element as an allowable stress load. So then if you do it LRFD, you still have to go back and do it allowable stress to get that reaction. Similar here, similar concept here. If you do it LRFD, you almost have to do it ASD as well, because you need to know parameters, stresses, reactions, so forth, and allowable stress. So I would say that by far the standard of the industry is to design timber in allowable stress. So save yourself some headache. It doesn't seem to be worth going into LRFD. But just wanted to point out to you that if you do LRFD, yes, you do get the tabulated value, and you do multiply it by those 3 factors that are shown there on the left of this table. Okay, getting back to the standard of the industry, using allowable stress design. So you're going to multiply that tabulated capacity, right, which would be then this one here. And by the way, this is covered in other tutorials in Bridging the Gap, where you find these values. So just if you don't find it, just leave a note afterwards, and we'll try to point you to the right direction. You're going to multiply that value then by the values in this column. And again, this is covered in other tutorial sessions in Bridging the Gap. And then we're going to come to, let me clear all of this. Then you're going to come to this set of values, which are in white. Between the ASD column and the LRFD columns, you find these capacity factors, capacity reduction factors. And these you would have to use either way, whether you're using allowable stress or LRFD design. And you can see that not all of these are applicable to every element or stress capacity that you are obtaining. So for instance, let me clear this. Let's just take what? Let's just take this here. This is the beam stability factor. All right. So if I am finding the capacity for flexure of my element, if I'm finding the allowable bending stress, do I have to use, did I do that right? Do I have to use the beam stability factor? Well, the answer is yes, right? It's listed there. However, let's just assume hypothetically that I am finding the tensile capacity of my element. So that's F sub T. I'm using this member in tension. So I need to find the capacity in tension, the tensile capacity. So I'm going to multiply my tabulated allowable tensile stress, which again, that's covered in another tutorial in Bridging the Gap. And I'm going to multiply it by each of these factors. So I'm going to multiply it not only by the load duration factor, but also C sub M, which is the wet service factor, C sub T, temperature, but notice how I don't need to multiply, I don't need to determine the beam stability factor. So it tells me, this table tells me what are the factors that I have to include in obtaining the capacity, the design capacity in tension for that element. Okay. Now let me also say this, because some of these look more manageable. You might say, well, gosh, finding the allowable bending stress, the capacity, the final capacity in bending sure looks tedious. Well, tell you what, some of these factors though do dissipate pretty quickly, meaning that they default to 1.0, so they're not really a factor, and you almost quickly know that, or you'll get a handle on that once you've done a couple of these problems. But that's also covered in other Bridging the Gap tutorials, so you can look for those, and if you don't find that, leave us a note and we'll try to point you in the right direction. But some of this defaults pretty quickly to 1.0, so it may not be as daunting as you might think. You don't have to sit there and write out, temperature factor, and here's the temperature, and here's the temperature gradient, and then finally you end up saying, okay, so therefore the temperature factor equals 1.0. Nobody's going to question you on that, you almost just ignore it. You just say, okay, so F sub B prime is equal to this times this, and you don't even include the temperature factor. So that's how quickly we can manage these in practice. For some of these values that almost by observation, you can determine what their value is going to be. But again, that's covered in another tutorial so that you know kind of which ones are when you need to bog down, let's say, and handle the temperature factor, and when you can just kind of gloss over it. Okay, and with that, we're done. So appreciate your time. Appreciate you giving us a thumbs up if that was helpful to you. If it wasn't, don't mind hearing the comment from you, letting us know how we can make these more helpful for you, how we can make these more transparent for you. Yeah, any comments, any suggestions would certainly be appreciated. And if you found value in that tutorial, certainly would appreciate you subscribing to our channel, so that you can then receive notifications of when we do put up design tutorials. All right, real good, thank you.